In this video, we'll look at models for statistical simulation, and we'll build a model to compare two populations. As music has gotten more portable, people are spending more time listening on headphones. Researchers have wondered whether this increased use might be leading to hearing loss. In 1995, they surveyed 2,928 teens and found that 14.9% of the teens had some degree of hearing loss. In 2015, they surveyed 1,771 teens and found that 19.5% had some degree of hearing loss. So we want to know whether there is a difference in the rate of hearing loss in these two populations, all of the teens in 1995 and all of the teens in 2015. In inferential statistics, our goal is to make an inference about a population parameter based on the statistic in a sample. In this case, there are two populations, so it seems like there should be two parameters: the percent of all teens in 2015 who have hearing loss, and the percent of all teens in 1995 who have hearing loss. But we're not interested in these parameters separately. We want to know whether or not there has been an increase. So what we do is subtract these two percentages to create what is called a compound parameter. And just to make things more compact, we'll write pi sub 2015 minus pi sub 1995 to represent this difference in percentages. Now, in our sample, the difference was 19.5% minus 14.9%, which is equal to 4.6%. The issue is that there is sampling variation. That is, if we looked at all teens in 2015 and randomly selected a sample of 1,771 of them, there would likely be a different percent that had hearing loss if we had randomly selected a different sample of 1,771 teens. Our goal is to quantify the amount of sampling variation, and the way we do this is by simulating many repetitions of the survey or study. This simulation involves making a model for the two populations. We're interested in two populations. One population is all of the teens in 2015, and the other population is all of the teens in 1995. To make a model, we need to specify the variable and parameter. First, we'll choose the variable. The variable is what we'll measure about each individual in the population. There are lots of things we could measure: whether or not the individual has hearing loss, whether they listen to music on headphones or not, or the number of hours they listen to music each day. Which one do you think we should focus on? In this case, we're interested in whether or not each individual has some degree of hearing loss. Next, we need to specify the parameter. Each population has a parameter: the percent of all teens in 2015 who have hearing loss, and the percent of all teens in 1995 who have hearing loss, and we subtract these to get a compound parameter. Then we need to specify a value for the parameter in our model. That is, we could specify that 2015 had a 10% larger rate of hearing loss, or a 4.6% larger rate, or that the two rates are the same, or any other percentage difference. Now, there are two ways to go here. If we use the idea that there is no difference between the percentages, then we could use a single model. And the other options would require us to use two models. We'll look at examples of both options. First, let's look at a model for a 4.6% difference. Pause the video and think about how you could model a difference of exactly 4.6%. It turns out the way to do this is to make what is called a bootstrap model. In a bootstrap model, you use the observed data as a model for the population. So in 2015, there were a total of 1,771 people in the sample, and 345 of them had hearing loss, and 1,426 didn't have hearing loss. So your model would be a list with 345 of the items corresponding to hearing loss, and 1,426 corresponding to no hearing loss. Similarly, in 1995, there were a total of 2,928 people in the sample, and 436 of them had hearing loss, and 2,492 didn't have hearing loss. So your model would be a list with 436 of the items corresponding to hearing loss, and 2,492 corresponding to no hearing loss. We'll start by building our two lists. For the 2015 list, we'll have 345 items for hearing loss and 1,426 items for no hearing loss. For the 1995 list, we'll have 436 items for hearing loss and 2,492 items for no hearing loss. Then our plan is to replicate the actual sample. So we'll select 1,771 items from the 2015 list and 2,928 items from the second list. Then we'll actually sample with replacement from the first list. And we can speed this up. And then sample from replacement from the second list. Now for 2015, 21.2309% of the 1,771 teens in the simulated sample had hearing loss. And for the 1995 sample, 14.1052% of the 2,928 teens in the simulated sample had hearing loss. So the difference in the percentages is 7.1252. But this is just one pair of simulated samples. So we can repeat this many times. Here we'll just simulate 1,000 pairs of samples. And then we can take each pair of simulated samples and compute the difference, taking the 2015 percentage and subtracting the 1995 percentage. Then we can look at a histogram of the distribution of these differences. In this histogram, each item represents one pair of samples of 1,771 teens from 2015 and 2,928 teens from 1995. And what is particularly important is that this was assuming that the actual difference in percent was 4.6 percentage points higher in 2015 than in 1995. If we had made a different assumption, then this distribution would be different. Now, let's take a look at the second type of model we could have made. Specifically, we'll look at a model for a 0% difference. Pause the video and think about how you could model the idea that there is no difference between the population parameters. The idea is that there is no difference between the populations. This is something called the null hypothesis, and the model we'll make will be called a null model. In a null model for comparing two populations, you combine the two sets of observed data into a single model. So previously, in our 2015 model, we had 345 with hearing loss and 1,426 without. And in 1995, we had 436 with hearing loss and 2,492 without. If our hypothesis is that the teens in 2015 and 1995 have the same probability of having hearing loss, then we combine these lists. So there are now 781 items for hearing loss and 3,918 for no hearing loss. Let's build this model and use it to simulate replicating the study. We'll start by building our list. We'll have 781 items for hearing loss and 3,918 items for no hearing loss. Then our plan is to replicate the actual samples. So we'll select 1,771 items for 2015, and then we'll simulate selecting the 1,771 teens from the list with replacement. And we'll repeat this process a total of 1,000 times. Next, we'll simulate taking a sample of size 2,928. And then repeat this a total of 1,000 times. Then we'll look at the pairs of percentages and compute the change in percentages for each pair. Then we can look at a histogram of the distribution of these differences. In this histogram, each item represents one pair of samples of 1,771 teens from 2015 and 2,928 teens from 1995. And what is particularly important is that this was assuming there is no difference in the percent of teens with hearing loss in 2015 and 1995. Now, let's do a quick recap of what we've seen here. Our goal was to make an inference about a population parameter. In our example, we had two populations. To make this inference, we needed to specify what variable we're looking at, the compound parameter we care about, and the value of the compound parameter we're hypothesizing. In our examples, the compound parameter was the difference in the percentage of teens that had hearing loss in 2015 and 1995. Then, depending on whether we hypothesized that the compound parameter was 4.6% or 0%, we created a model, or two, to reflect this hypothesized parameter value. And then we used a computer to simulate repeating two samples of size 1771 and 2928 and computed the difference in percentages. And this overall method will be central to the way we make statistical inferences for two populations.